We're going to take another look at the period of a simple harmonic oscillator, but this time we're going to look at pendulums. We already know the period for a mass spring system, omega, the angular frequency, or period, are things that we've calculated. And so what we want to do is kind of do that same differential equation process for a simple pendulum, which is the big one. Also a physical pendulum, where it has some moment of inertia that can't be described by just a single mass, and a torsional pendulum, and see how they all kind of follow this same process. So a simple pendulum, right, is just a mass attached to an ideal spring where it can't stretch and just swings back and forth. A physical pendulum is something like hang a ruler from one end and let it swing, basically where you cannot consider the part of it that's connecting to the mass at the end as massless. So that would be, a meter stick from one end. Even if you've ever looked at a grandfather clock, the pendulum in there swinging back and forth, one of those big ones, is not just a ball at the end of a string. It's, a physical object which has different spacing. The torsional pendulum is something that sort of twists back and forth between, instead of, an angle this way, it's an angle this way. So we're going to start with F equals ma again, or torque equals I alpha. We'll write down the differential equations. We're going to do a small angle approximation when appropriate, and we can test it. The basic idea is that in radians, the sine of an angle is about the same, right? So about 10 degrees is a good example. If you do the sine of 0.17 radians, you get about 0.17 radians. So to recap, simple harmonic motion goes like x max, the amplitude times the cosine of omega t. We'll leave off the phi for now because we're not really worried about it. And the second time derivative gives us the acceleration, gives us this omega squared. We can also do that in angular quantities with torque. That's fine as well. So for the spring mass system, we did this in the last video. Omega equals the square root of k over m by solving that differential equation. For a physical pendulum, you have basically the same idea, but now instead of force equals ma, it's torque equals I alpha. That's the second time derivative of theta. We've got mgh over I, and we're going to use a small angle approximation here just to get theta. And when we solve that, we get omega equals square root of mgh over I, or period equals 2 pi times I over mgh. And so what we see is that the moment of inertia and how much total mass there is are what matter for solving this. For a simple pendulum, again, we're going to use that same small angle approximation, and we get that same basic relationship. Here we get the square root of L over G. With a torsional pendulum, net torque, again, here we're just dealing with the kappa and theta, and we end up with 2 pi times the square root of I over kappa, where kappa is basically the stiffness of the spring or of the wire as you spin it back and forth. So what do we have? Spring mass, simple pendulum. Those two are on your equation sheet. Those are the two you use most often. The physical pendulum, it's good to notice that in addition to caring about the mass, there's going to be mass inside that I, right? It cares about the distribution of the mass. So you really do need to know the moment of inertia to solve that one. The torsional pendulum, also not on your equation sheet, but helpful to think about when we're thinking about different things that can oscillate. So the period of a simple pendulum. How does this change if you double the mass, double the length, right? What about taking a pendulum clock to a place where the acceleration due to gravity is different, like on the moon, right? These things are important to know. So let's do an example. Zing builds a simple pendulum clock. Sadly, the clock runs too slowly. So 60 tick-tocks, which should be 60 seconds, actually takes 63 seconds, right? So that means the period of this clock is actually 1.05 seconds. What's wrong with the clock? Well, the clock is running too fast, right? Period is too slow. The period is too long. And we know that L, we could find that. We need to shorten the length of that so we can shorten our period by a little bit. Right? Here we're looking at how long should the simple pendulum be to keep correct time. There's another thing to think about here, and we've talked about this a little bit. When you are going up and down in an elevator and it's accelerating, we feel as though our weight changes, but really it's just the acceleration of the system. And when you're in an accelerating reference frame, we can think about what is the effective G? What does it appear that little g is like? And when we do that, right, if it accelerates up at positive 5 meters per second, it's, if you think about dropping an object and measuring its acceleration toward the floor relative to the elevator, it would be down at negative, or it'd be down at 15 meters per second. So it would act as though we were on a planet where g was negative 15 meters per second. And so we could use our formula and use this effective g, what it appears g is doing, and the period would be faster, right? And that makes sense because basically what you're doing is you're pulling up on that pendulum, right? Making that tension be even bigger than it normally would be as it swings through, causing it to swing faster, right? There's no experiment you can do that will tell you whether you're actually in an elevator accelerating or if there's actually a different G. Of course, knowing that you're on the planet Earth would tell you, but you can't tell that just by using a device. So that's the end there. This is a fun one because it's just like the experiment we just did. And so we'll talk a little bit more about what we can use a simple harmonic oscillator to do next time.